Hello, I'm Roger de Paz, and this is the research I have been working on with the NICKEFFECT project, focusing on the electrodeposition of nickel tungsten films and the study of its electrocatalytic properties in acidic media and durability. First, I will run a brief introduction, then I will explain on the aim of this project, and then I will focus on the results obtained to finally reach a few conclusions. With an increasing demand to transition from fossil fuels toward renewable energies, the need to obtain an efficient method to storage energy is of the highest importance. Hydrogen production through water splitting via electrocatalysis is one of the more researched methods due to its relative simplicity. We only need 2 electrodes in a water bath to split water and store the energy as hydrogen. Nowadays, the most efficient electrodes toward water splitting contain platinum or other noble metals from the group due to their high efficiency. The problem is that apart from being a scarce resource, they are needed in growing demands, as we can see the predictions for the production of fuel cell electric vehicles, being this only one of its many uses. Looking again at the volcano plot, we can see why nickel is a very good option, since it has the best catalytic properties after the noble metals. We decided to alloy it with tungsten because of 2 possible effects. The resulting alloy exhibits increased corrosion resistance, and second, tungsten acts as a catalytic activator towards hydrogen evolution reaction. So, the objectives of this project are to alloy nickel with tungsten in film form by electrodeposition to improve the catalytic activity and durability of pure nickel while replacing platinum, to test the performance of nickel-tungsten films towards hydrogen evolution reaction in acidic media, and to optimize the catalytic and durability properties of the material by machine learning. For the deposition of the films, we used the following gluconate-based bath. A standard 3-electrode cell was used to deposit the samples using silicon chips with sputtered titanium gold layers as a working electrode. As a counter electrode, we used the platinum wire, and the reference was silver chloride. Here you can also see the cyclic voltammetries of the bath at several temperatures. First, we did a screening depositing samples at several temperatures and current densities. As you can see at the table, the amount of metal deposited increases with temperature. On the other hand, the tungsten content of the sample slightly decreases. Having said that, all samples have a similar tungsten content ranging from 10 to 12 atomic % of tungsten. As you can see in these same images, we can obtain different morphologies with just changing the deposition conditions, going from a nearly smooth sample to acicular grain films, and finally to nodular grains at high temperatures and current densities. So even with a nearly the same concentration of tungsten, we can modify the surface of the samples, which is a key parameter for catalysis. The crystallographic structure of the nickel-tungsten coatings was studied by X-ray diffraction. The pattern shows peaks compatible with the face-centered cubic nickel phase. We can also observe that the nickel peaks are shifted towards lower 2 theta angles due to the incorporation of tungsten in the lattice, in the form of a solid solution. The crystal size estimated from the full width half maximum of the 111 peak using the Scherrer equation is between 4 and 5 nanometers, indicating the nanocrystalline character of the film. Linear sweep voltammetries from 0 towards minus 0.6 volts were performed in 0.5 molar sulfuric acid at 25 degrees, for samples deposited at different current densities. The samples with the best performance at minus 10 mA centimeter square during the measurement, both at the first cycle and after 200 cycles, was the sample deposited at minus 4.8 mA centimeter square. The performance of the samples was tested versus a sputtered nickel substrate that has one of the worst values, and also it did not resist the full 200 cycles. After obtaining the optimal current densities to deposit the film, we went back to further study the morphology of the samples, since, as mentioned before, there's a big difference between the morphologies of the substrates, once observed at the nanoscale with SEM. The electrocatalytic surface area of the samples was measured, obtaining the expected results, where sample at 25 degrees has the lowest EXA due to the smooth surface, and sample has the highest due to the acicular grains. After analyzing the potentials obtained from the linear sweep voltammetries, we could obtain 2 conclusions. The best performance was obtained at 50 degrees, and the samples at 25 and 65 have a lower resistance to the acidic media, since as we can see in the graph, there is a big variability between the first linear sweep voltammetry and the 200th. After the linear sweep voltammetry, the sulfuric acid was analyzed by ICP to determine the amount of metals leached. As you can observe in the table, the highest amount of leaching can be observed at the sample at 65 degrees. Having said that, the amount of leaching was very low on all nickel tungsten films at the ppb level. Finally, with the help of mechanics, we devised a method to optimize the catalytic properties of the films and durability. First, we fed the obtained data from previous results, and after the calculations, the machine learning suggested more experiments to look for the best deposition conditions. We optimized the current density and deposition temperature to obtain the lowest Tafel slope and over potential at minus 10 milliamperes centimeter square during measurements, both at the first and 200 cycle, to also obtain insights on the durability of the material. In these graphs, you can see the actual measurements and how the program nails down the best parameters. So after around 30 suggested trials out of thousands of options, the best sample was the one synthesized at minus 9 milliamperes centimeter square and 62 degrees. Here you can see the improvement versus the first suggested best sample at minus 4.8 milliamperes centimeter square at 50 degrees in blue, and the machine learning optimized sample in black. As you can see, at first both have similar Tafel slope and over potential. But after 200 cycles, while the blue sample degrades a bit, the machine learning optimized sample shows even a better performance than the initial one. Having said that, both samples are much better than the pure nickel electrode deposited sample in purple. Finally, to further analyze the durability of the samples, we ran a long-term chronopotentiometry at minus 10 milliamperes centimeter square for 7 days with the machine learning sample. As you can see, there's a slight decrease in potential for the first 2 days, but then the sample stabilizes. We also measured the liquids of the sulfuric acid to quantify the leach metals. We can observe that the amount of leach metals in the acid decreases, suggesting a redeposition on the substrate. Same images before and after show the circular morphology with no changes after the 7 days. To conclude, we were able to deposit nickel tungsten films with a fixed tungsten content around 12 atomic percent, also obtaining different grain morphologies, changing the current density or the temperature. The samples have a better performance towards hydrogen evolution reaction in zinc media than pure nickel. Thanks to the machine learning, the film deposition conditions have been optimized to minus 9 milliamperes centimeter square and 62 degrees. The durability of the films has been severely increased thanks to the tungsten co-deposition, and finally the films show high durability in acidic media, enabling hydrogen evolution reaction for at least a week. This work has been funded by the NICKEFFECT project from the European Commission. Thank you all for listening.